waves can either be in phase, as they are here, or they can be out of phase, as they are here. And it's this phase difference that's actually the bit that does the quantum mechanical calculation for you. But what you're able to do is you're able to change this phase difference by applying the field, as I said. And what this corresponds to physically is when you apply a magnetic field to the qubit, a current starts flowing around the loop. And so I don't know if you can actually see this very well, but in this state here, which I've denoted state 0, the current is flowing clockwise around the loop, and the magnetic field is going downwards into the slide that way. And in this one, the current is flowing anti-clockwise around the loop, and the magnetic field is coming out the other way. So by changing the magnetic field, you can change the current flowing around the loop. And if you choose just the right magnetic field, you can get the current flowing both ways around the loop at the same time, and this is when the system is in a quantum superposition of the states 0 and 1. So we represent the state 0 and 1 as the current flowing either way, or analogously the magnetic field going in or out. So you can see how this is similar to an NMR system. You've got a very small magnetic field pointing either up or down. So again, it's very similar to that case. And you can have it pointing up and down at the same time in the superposition of the states. This is an energy diagram that shows the energy of the system as you change the phase difference across this wave function. So basically, as you apply the field, you change this phase difference and you get into a state where the 0 and 1 are just equally favourable. They have the same energy, so the quantum system just falls into a superposition of both states at the same time. Okay? And the interesting thing about this is they're no longer considered separate states, because these states sort of quantum mechanically link across the barrier, so the superposition is now a state in itself. It's no longer a 0 or a 1, it's a 0 and 1 at the same time, and that's quite important. Okay, so why superconducting flux qubits? Why is this system so interesting and important? You can actually make these type of qubits using existing process technology. So you could go to something like a semiconductor foundry and you can give them a design and they'll make it for you. And this is quite important because getting something out of the research lab and getting it into commercial fabrication is actually quite a big step. So this is a process that's actually already compatible with that large-scale device manufacturer. It's also compatible with other types of superconducting electronics and superconducting logic, which has been shown to have much higher potential clock speeds than conventional silicon. So this kind of logic, you're talking about hundreds of gigahertz potential operating speeds, as opposed to what we're being limited by at the moment in terms of conventional silicon logic. And like I mentioned earlier, these systems are quite unique amongst the qubit family because they contain what's known as a macroscopic quantum superposition. So if you put an atom into a superposition of two spin states or use two of its energy levels, you've just got one atom, and that's a very small system. In this case, you've got this huge loop of material. This is huge compared to the scale of an atom, and the whole thing is in a quantum superposition at the same time. So you can kind of see why I might think this is important. If you're trying to scale up quantum systems to larger and larger sizes, then something like this is quite a good candidate for starting to build large-scale quantum systems. The disadvantages of this technology is that you are required to cool them, and I'll show on the next slide why. Although the cooling techniques are actually improving faster than this technology anyway, so people are now miniaturizing fridges and things, and you're able to cool these things much more easily than you could 5 to 10 years ago. So that technology is actually improving as well, so it's not too much of a problem. And the final issue is that these kind of solid-state qubit systems that you build in a similar way to semiconductors are very prone to decoherence, which I'll talk about a bit later on. So just a quick slide to show how these things are made. Here is a schematic of what a Josephson junction actually looks like in terms of the materials. So you put down a piece of superconductor, you then make a weak link between another piece of superconductor and this one, and this is usually a little bit of insulating material or something like that. And you can connect electrodes to this to measure it in the same way that you would with a conventional silicon chip. You can also use different types of superconductors to get different effects and things, but that's not too important. Okay, so what temperature do these things work at? Well,
I was wondering, because you said that fridges are getting smaller and smaller.
Yeah.
Is this the kind of fridge I've got in my kitchen?
No, this is a much larger refrigerator, and it goes to much colder temperatures. To start with, the device actually needs to be superconducting. And I don't know how much people know about superconductors, but they tend to require quite low temperatures to become superconducting. So the one that's used most commonly to make qubits is niobium, and that has a superconducting temperature of below 9 Kelvin. So you actually need to cool the system with liquid helium to get the thing superconducting in the first place.
So 9 Kelvin is what, minus 260 degrees centigrade?
Yeah. And so, but that's not the only problem, because it doesn't just have to be superconducting, it has to maintain the quantum coherent state. And the problem is, once you've got this state with your two different sort of up and down spin, or whatever you want to think about, if you have a thermal environment surrounding it, you can actually excite one state into the other if the energy that comes from the temperature of the environment is high enough to excite the state over this small energy barrier. So what happens in this case is that the thermal environment just drives the qubit from one state to the other without any particular, at random. So then your qubit superposition just becomes all messed up, because what's happening is your environment is essentially kind of making a measurement on your system by disturbing it. So here is the qubit myth, which is that everyone thinks, okay, if we have room temperature superconductors, we can make room temperature quantum computers. But that's not true, because even if it's superconducting at room temperature, you still need to cool it down much, much lower so that this thermal noise doesn't affect qubits. Okay. So here's a picture of a qubit inside a copper box, which is for shielding, and I'll talk about that in a little while. And this copper box is stuck onto the end of what's known as a dilution refrigerator, and this is apparatus that we use to get down to very, very low temperatures indeed. So we take the qubits down to below about 30 millikelvin or something like that, which is 0.03 of a degree above absolute zero, and at that temperature they work well and they form nice quantum states. So these are the temperatures that we work at in this particular system. Okay, so away from qubits for a while, I'm going to talk about quantum computing in general. So what can quantum computers do, and why are they so interesting? Well, the power of the quantum computer comes from the fact that it can exploit these concepts of entanglement and superposition. And because qubits can be put into superpositions of states, the idea is that they can then explore different calculation possibilities at the same time. So to illustrate this, I've got a little cartoon here, which shows a classical register, you might imagine being part of a classical digital computer. So if you wanted to do some calculations, you might want to calculate all the possibilities you can have just using 2 bits. So in the first state here we have the zeros, and then in the second computational step you can calculate a 0 and a 1, and then a 1 and a 0, and then a 1 and a 1, and that then fills up your register. However, it does take 4 computational steps to do that. If you have a quantum register, you can do it in a single computational step, because you can just take your 2 qubits and you can, because they're in a superposition of 0 and 1 at the same time, they can calculate all these possibilities in a single computational step. So that's kind of like a schematic explanation of where the power comes from. By exploiting this superposition of states, you can do things quicker. The other interesting thing about quantum computers is that they can natively store the states of quantum objects. So if you're trying to model a system of some spins on a molecule or something, those spins are naturally quantum objects. So if you can model their quantum states using qubits very naturally, If you try and model the quantum states using a digital computer, you have to do things like solving the Schrödinger equation, using all kinds of